8:27 p.m. on our clock of the Earth's history, 650 million years ago. The planet faced climate disaster, a global deep freeze. But what made it happen? Snowball Earth wasn't the first time the Earth had frozen, and it wouldn't be the last. Our planet goes through an ice age about once every 100,000 years. Most of them are caused by changes in our orbit. The further away from the sun we go, the colder it gets. At the height of the last ice age, ice sheets covered around a third of the planet, and all of this would have been buried under hundreds of feet of ice. But factors like orbit and rotation aren't enough to explain ice stretching right down to the equator. That must have taken something far more dramatic. The smoking gun turned out to be our atmosphere. Specifically, greenhouse gases like carbon dioxide.
A greenhouse gas is any kind of gas which has the capacity to convert the sun's rays into heat, making this planet the warm planet that it is today.
But it's a delicate balancing act. If CO2 levels grow too high or too low, the climate spirals into chaos. Too much carbon dioxide and the planet warms, too little and it cools.
Carbon dioxide is a very important gas. It's both our dilemma and our solution when it's there in too great a proportion that overheats the Earth, which of course we're worried about today. However, in the time leading up to Snowball Earth, we had the opposite problem. There wasn't enough carbon dioxide, and the Earth began to cool to a point where there was a runaway refrigeration that locked this Earth up in an icy crust.
Gehling believes that a drop in carbon dioxide levels caused the Snowball Earth disaster. Something was removing the CO2 from the atmosphere on a huge scale. And there's only one process capable of doing that: weathering. Carbon dioxide mixes with water vapour to form acid rain. The acid reacts with the rocks it falls on to form new carbon chemicals in the water. It then washes down to the sea, where it helps form solid limestone. Carbon dioxide that was once in the atmosphere is locked away on the ocean floor.
When weathering occurs at a great rate, you strip away rocks with acid rain, and that takes carbon dioxide out of the atmosphere and makes sure that it's locked away in the ocean.
Weathering happens more quickly when it's hot and humid. Normally, at least some of the Earth's land masses are too far north or south for weathering to be a major factor. But 650 million years ago, all the Earth's land masses from Death Valley to Australia were clumped together into one big supercontinent at the equator. The weathering process went into overdrive. CO2 levels crashed, and so did the Earth's temperature.
You have carbon dioxide being taken out and not replaced, and as a result, the Earth inevitably has to cool until you have a snowball.
Today, plants and animals help balance the levels of carbon dioxide in the atmosphere. Plants absorb it, animals breathe it out. But 650 million years ago, the only life forms on Earth were single-celled bacteria in the oceans. And they were actually making the situation worse.
650 million years ago, this is a world of cyanobacteria. Bacteria that formed a slime layer on the seafloor. Cyanobacteria are tiny organisms that have been around on this planet for 3 billion years before Snowball Earth. But At this time, they were particularly important.
These cyanobacteria sucked even more carbon dioxide from the oceans and locked it into limestone reefs called stromatolites. Some of this ancient carbon dioxide is still trapped in fossilised reefs, like these in Flinders Ranges in southern Australia. When Jim Gayling pours a weak acid onto them, the carbon dioxide they locked away hundreds of millions of years ago fizzes out.
What you'll see is an effervescence. Those white bubbles are carbon dioxide that had been locked up in these stromatolites, being released back into the atmosphere.
Rather than stabilising the carbon dioxide levels, the cyanobacteria were depleting them further. In combination with weathering, they sucked the carbon dioxide out of the atmosphere and temperatures plummeted. Even then the planet might have avoided a total freeze, until a catastrophic chain reaction pushed it to the point of no return. Seconds past 8:27 p.m. on our clock of Earth's history. Snowball Earth, 650 million years ago, and counting. Ice was creeping down from the poles. In a normal ice age, at some point it would have stopped, but this wasn't normal. The ice just kept on coming, until eventually it reached a point of no return. As it did, it triggered a phenomenon that would push life to the limit. The Earth's surface is made up of land, open ocean and ice. These surfaces all reflect sunlight differently, and that's the key to what happened next. This is the Arctic Ocean, at the point where the ice meets open water. Scientists call it the lead edge. And geophysicist Perovich is here to study how the ancient Earth tipped over into a catastrophic deep freeze.
This is the place where the ice that's frozen to the shore meets the open Arctic Ocean. But it's more than that. The lead is where there's water, the lead's where there's light, and so the lead's where there's life. We see whales going by and seals, and birds flying above. It's an incredibly productive area.
Here, Perovich can compare the reflectivity, or albedo, of two very different surfaces, the sea ice and open ocean. His sensor measures the amount of sunlight hitting the ice and the amount it reflects back. Sea ice is the most reflective surface on the planet. It reflects 85% of the sunlight that hits it.
If we were to just go out there, just 100 yards away to the lead, the albedo would be less than 10%. And what's interesting about this is this snow-covered ice has the largest albedo of any naturally occurring surface on Earth, and the open ocean has the smallest. So right here, we have a contrast between the best natural reflector and the worst natural reflector.
Open sea reflects very little light back into space. It absorbs the energy in the sunlight, keeping the planet warm. 650 million years ago, the opposite happened. Earth's best reflector, sea ice, was replacing its worst reflector, sea water. When enough ice had formed, the remaining ocean couldn't absorb enough heat. So more sea ice built up. That reflected more sunlight, the Earth got colder, and that made still more ice. It was the point of no return.
Let's say we grow a little bit more ice. So we're replacing the worst reflector with the best reflector. will cool things off, and we'll get more ice, and we'll cool it off more, and it builds upon itself.
A runaway freezing effect capable of turning the whole planet into an ice ball. It's an idea no one even considered until a few decades ago. Scientists only discovered it was possible when they were studying another kind of disaster altogether. A nuclear war. During the Cold War, researchers predicted that a nuclear holocaust could push enough smoke and dust into the atmosphere to block out the sun and initiate a global freeze. Russian climate modeller Mikhail Budyko was investigating this scenario when he made a chilling discovery. He calculated that if the ice sheets spread beyond 30 degrees latitude, that's as far south as North Africa, they'd reflect so much of the sun's energy that the Earth would reach an irreversible tipping point.
So when we have a system like the Earth with these feedbacks, one of the things that's talked about a lot is tipping points. You can think of it as you're in a boat rocking back and forth, not much changes until you go too far, and then you're in a new state. And Budyko's work said that if we move the ice down far enough, we'd reach a tipping point and cover the whole Earth with it.
Budyko calculated that if the ice ever reached this tipping point, the planet would no longer absorb enough heat to keep the ice in check. The planet would be entombed in ice from pole to pole. The theory is that 650 million years ago, this was exactly what happened.
Instead of the world we have today, we'd have something that looked like this. A vast expanse of white, of blocks of ice tilted every which way, covered by snow.
The planet descended into the most extreme and least hospitable climate it had ever experienced. Eventually, the ice sheets collided, clamping their icy jaws shut at the equator. It seemed that nothing could survive in this frozen wasteland. And yet, incredibly, it was this catastrophe that brought about life as we know it, and without it, none of this and none of the people around us would be here today.